Okay, so this video we're looking at non-linear velocity time graphs. So previously we looked at linear, so straight line kind of graphs, velocity time graphs, but now we're looking at non-linear. So just to recap really quickly again, right, hopefully from the last video we know, and this is really important, this is absolutely fundamental for a velocity or a speed time graph, that the gradient is acceleration. So how steep these lines are here represent acceleration, and area under the graph represents distance. These are two really key things we can get from a velocity or speed time graph, okay? And this is an example of a linear velocity time graph because it is all straight lines. But today we are looking at getting the acceleration and distance now when the graph is not linear. So for example here, how would you get the acceleration of the speed time graph or the velocity time graph? They mean the same thing really, or think about it meaning the same thing. When we've got kind of non-straight lines, it's non-linear. Well, to find the gradient, to do that, to find the gradients, we need to find the gradient of a tangent at a particular point. Okay, so let's say we wanted to find the acceleration at time is equal to 3 seconds. So this point here, okay, I would have to go and put my point up here at 3 seconds and then draw a tangent line, okay? So remember, a tangent is a line where you're trying to roughly match the gradient at that particular point, and it must only touch at one particular point. So that's a pretty good estimate for a tangent line. That would be a shocker because it's got to be close to the gradient at that particular point. So it's got to be roughly something like that. So we have to find the gradient of the tangent at a particular point to estimate the acceleration when we've got a non-linear curve, speed time graph. Okay, what about distance? So if we wanted to find the distance, which means the area under this graph here, if it's non-linear, you've got to divide up the area into triangles or trapeziums or rectangles or any shape that's going to best estimate the area. So you can see here, right, we can't find the exact area because, like, how can you find the area? Well, you can find the exact area using something called integration, which if you do A-level maths, you will see. But from what we currently know, we can't exactly get the area of everything here as well, can we? So we've got to estimate it using shapes that roughly fit the shape of that curve. Okay? So that's really important. We can estimate acceleration by getting a tangent line and distance by splitting up your area into shapes that roughly match the organic nature, okay, of that curve. Okay, terribly drawn in there, okay? Right, so let's look at an acceleration example. So it says find the acceleration at time t is equal to 7 seconds. So first of all, you've got to identify, or time is 7 is there. We're looking at finding the acceleration at that particular point there. Okay, so, and again, right, if you didn't know that acceleration was the gradient of a speed time graph, it doesn't really matter. It's just knowing, more importantly, right, that, rate of change or gradient is what I'm after at a particular point. So I've got to go and draw in a tangent line that roughly matches the gradient at that point. So something like this here, okay? And then to get the gradient of a tangent line, I'll just go and pick 2 points on that line. There could be any points. You could go for this point and this point here. Or actually, that would be bad points to go for because you want the points to be easy to read. So what have I gone for here? Okay, they've gone for literally the 2 endpoints. Probably because there's not yet. So with this, I always usually say go for a point that goes exactly through the corner of a square. But apart from the endpoint, there are no other ones to go through the corner. So they've just gone for the last point and the top point. But you could go for any 2 points. It makes no difference. And then you draw in your triangle. Okay, so what I would do here is, what you should do is draw in your triangle. And you should use a ruler to make this really accurate. But that will do. And let's go down from here. Okay, and they're saying, well, gradient is rise over run. So this top point here is 35. And the bottom point is going to be 6, which is down here. So the rise is going to be 35 take away 6 will give you that height. Okay, so 35 take away 6 over the run, which is saying, well, this endpoint here is 12. And we're starting at approximately 2.3. We can't say what it is exactly, but roughly that point there is 2.3. Hence the run is 12, take away 2.3. If you do that, you get 2.99. So really it's an estimate for the acceleration because depending on how you draw your tangent line, you might have drawn your tangent line slightly different, something like that, which means of course you would get a slightly different gradient or acceleration. So it is an estimate, which is important to bear in mind. Okay, so that's how you find the acceleration from a nonlinear speed or velocity time graph. what about distance now? So it says estimate the distance traveled over the 12 seconds using 4 strips of equal width. Okay, so that's really important, right? Because we're using 4 strips of equal width, okay? Well, I'm going from 0 seconds to 12. I've got to break this up into 4 strips. I've got to do 12 divided by 4. I'm doing intervals of 3, so 3, 6, 9, and 12. Each of these shapes here, they've got a base of 3. Right, now what I need to go and do is, and I've drawn in some shapes here that roughly match the trajectory of that shape. You know, if I go back to this, you know, and if I went and drew in, let's say, a rectangle here, so like this for the first one, and then across, and then down, right, is that going to give me a good estimate for this area? Because ultimately, I want this area here. Is that going to give me a good area? No, because I'll be getting all of this extra excess. That is a pretty bad estimate. So you've got to choose a shape that's going to roughly, okay, match the trajectory of this curve. So a triangle is a pretty good bet for that first one. And then between 3 and 6, right, again, or maybe you're thinking potentially, right, you could have maybe gone for a rectangle, something like that. It wouldn't be the worst estimate. You know, you've got a bit of excess over here, okay, and you're missing a bit over here as well. But actually, right, what they've gone for here is they've gone for and it is a trapezium. So they've gone for this, okay, which I'll go and get up in a second. That is a better estimate because you're only missing out on this part here. And similar here, you're only missing out on this part here. So let's just get it on the screen because it's just much neater than me trying to get it in with all my drawings. But yeah, so there we go. They've gone for a triangle, a trapezium, another trapezium, and a triangle. And that's a pretty good estimate. You can see we're only kind of missing out on little parts of the curve. Anyway, let's go and get the area of each shape. So let's begin with getting the area of this first shape 1. So that is a triangle. So the area of a triangle is going to be the base, which is 3 across. So 3 times by the height of the triangle, which is equal to 35. And then we've got to divide it by 2 because area of a triangle, we need to half it. So 3 times 35 is 105 divided by 2. 3 times 35 is divided by 2 is equal to 52.5. So 52.5. And a unit is going to be, or distance area is going to be meters in this case, because we're looking at meters per second. So meters on the first one. Good. Area of shape 2, which is going to be this one here. Right, shape 2 is a trapezium. Right, and if we don't know the formula, or if we need reminding, that's pretty important. A trapezium has 2 parallel sides, which we go and call A and B. Let's go and draw it in a different colour so we can see that's the formula that we're after. So a trapezium, something like this, right? Okay, where we've got A and B are your 2 parallel sides, so these ones here, and then the height of it is this bit here. And the area of a trapezium, so area, and you need to know this off by heart, is you add the 2 parallel sides, so A plus B, you times it by the height of your trapezium, and then you divide it by 2. Okay, so to get the area of shape 2, we've got to go and do A is going to be equal to A plus B. Well, let's just go and call this side here to be side A, and this side here to be side B. Okay, in this case, so A has got a height of 30. Okay, so it's going to be 30 plus the height of B, which is 35. Okay, times that by the height. It looks a bit strange. Basically, it's a rotation, this trapezium. Okay, so the height now is this bit, which is going from 3 to 6, which is a height of 3. Timesing that by 3. Let's put that into a bracket. That's what I should really do. And then we are dividing that all by 2. Okay, so 30 add 35 is equal to 65, times it by 3, 195 divided by 2 is 97.5 meters. Okay, for area 2. We then got shape 3, which is another trapezium, right? And I'm going to get rid of these bits, otherwise it might get in the way. Let's go and call this side now side A, this side B. So again, area of a trapezium, it's going to be equal to, well, the height of A is 15. So 15 add B. B is now got a height of 30. So 30, and I've got to go and times by the height of it. The height is going from 6 to 9, which is just 3. So times it by 3 over 2. And then let's go and put that on our calculator. So 45 times 3 is 135, divided by 2 is equal to 67.5 meters. Okay, and last but not least, we've got another triangle, which is nice and easy to get. So the area is going to be the base, which is 9 to 12, which is 3, times by the height of that triangle, which is going up to 15. And I've got to go and half that, divide that by 2. So 3 times 15 is equal to 45, divided by 2 is 22.5, so 22.5 meters. And now, right, all I've got to go and do is add together all of my individual parts, so add these together. And if I do that, okay, I'm just going to go and reveal it from this here. So if I do that, I will get 240 meters. This has just done it for me. So 52.5 at 97. Let's double check it. 52.5 at 97.5. 67.5 at 22.5 is equal to 240 meters, which is exactly what they've got down here, which is always good to know. So that's really good. That is our answer. Okay, this here is the same thing. They've just worked out in one go. So that's the area of number 1. So that's area of shape 1, shape 2, just written a bit differently. It means the same thing. Shape 3, and then shape 4. Okay, hopefully that was useful, and that is it for velocity time graphs. Thank you.